Hello everyone! In this video series we'll try to drive and test this small 7 segments LCD display. I will be using Titan LCD driver for these purposes, and everything will be driven by STM32 microcontroller. We'll also be using STM NUCLEO board in order to debug our application, and this will help to test our LCD driver. Also, we'll be designing special PCB which will be pluggable into NUCLEO board. This way we could debug everything. We'll also be covering components layout overview and assembly part with components placement. Then we'll spend some time trying to solder everything together, where we'll have a combination of SMD and through-hole parts. And we'll be making everything compatible with STM NUCLEO board, so we could plug it and make proper testing and debugging. Also, we'll be covering how to make debug session using STM32 CubeIDE. This will help us to check that everything is working correctly. So let's start with our LCD component itself. Here on AliExpress you can find it for just $1. And the main specification can be found below. We need to pay extra attention on operating voltage level, which is exactly 3 volts. Here we also need to know LCD operation duty cycle and operating voltage BIAS level. Duty cycle will give overall sense in terms of how long each LCD segment will be ignited. In case of 1 quarter, each segment will be activated only 25% of the time. This will allow one single pin to drive 4 segments, where each of the segments will be on for just 1/4 of the duty period. Like here, pin number 6 can drive 1D, 1E, 1G and 1F segments. This can be achieved by having 4 separate command lines, where each of them will have special modulation, which will act like a multiplexer switch, enabling specific segment to be active on just 25% of the time. As you might know, we cannot drive LCD segments using direct current, and the same is applicable to our small LCD component. Segments will not be ignited if we'll apply constant 3 volts between common and segment pins. In order to ignite segment, this should be AC, and this should be above specific amplitude threshold. So, in case of we'll apply alternative current, but this will be below threshold level, then LCD segment still will not be switched on. And this principle is used for our multiplexing logic, with help of 4 command lines. In case of you would like to switch off all available LCD segments for a specific pin, we just apply in-phase signal in relation to our command line strobes. And, as a result, we'll have the following voltage difference between segments and the command line. As you can see, AC voltage amplitude will be below threshold level. This way all segments will be switched off. And if you would like to switch on specific segment, then we can apply signal inverse operation on a specific time section. This way voltage difference will exceed defined threshold level. Hence, the segment with such voltage difference will be ignited. All of this common and pin signals generation will be responsibility of LCD driver. For these purposes, we'll be using Titan LCD driver, which supports 4 command lines and 1/2 voltage BIAS level. But what this BIAS level actually means? In our world, we are working with digital domain, so we'll not have perfect sinusoidal waveforms for our LCD driving signals. They will be defined by discrete values. And appropriate BIAS level will indicate how many distinct voltage levels will we have. Like 1/2 voltage BIAS will let us know that there will be 3 distinct levels. In case of 1/3, there will be 4 levels. And this is our LCD driver datasheet, which contains a lot of useful information. With help of Google Translate, we can get an English version here. The first diagram allows us to understand driver chip's pins layout, so it will be quite helpful when we'll be designing PCB schematic. And these are primary pins with functionality description. The main concept here that we'll be sending certain commands and data to the pin number 12, while output pins will take the full responsibility to drive LCD command and segment pins. And the set of available commands themselves, we can find them starting from the page number 5. Here you can refer the sequence diagram, how the data and command streams can be submitted. Initially we have to submit system-enabled command, then we can configure our BIAS level with 4 command ports, and lastly we just need to call LCD on command. From this point we can submit corresponding 4 bits data chunks. This will define which LCD segments will be ignited. You can use this memory map to establish which segments should be lit up. Please note that segment pins will start with number 9. And our timing diagram shows how the data chunks can be transmitted. These can be sent one by one, either in bulk with incremental addresses. Now we can spend some time on microcontroller selection. I do prefer to use lcsc.com website. It has quite good variety of selection and quite convenient filtering UI. Our target here is STM microcontroller. Below we can find some of them which already have LCD driver integrated, but I'm looking for a bit cheaper option. So, as a 32 bits microcontroller, I would choose this one, and stock availability is more than 70,000 here, which is quite decent. As a development board, I would like to select this NUCLEO F030R8 product. This will help me with development and debugging process. MCU used here is also quite suitable for our application. We can notice here that this board consists of 2 parts. The top one is responsible to establish SWD debugging protocol with your PC, while the bottom one has our target STM chip itself and few peripherals. During our PCB layout design, we have to know exact distance between connector pins. So this development board has exact number of 2300 mils between them. In order to use this board for debugging purposes, we just have to plug it to PC using this USB connector, and this will be automatically recognized by STM CubeIDE. Now let's review adapter PCB which will be pluggable into this development board. Here we have its schematic. On the right side we have 2 main connector sockets. They will be responsible to establish NUCLEO board connectivity with LCD driver. 2 pins are used to provide power supply, 1 pin will be used to transfer data chunks to LCD driver, and few more control pins to interact with the driver, like chip select and write signal. Reset and count pins will have dedicated buttons to allow users input. We will be using them for debugging purposes and to reset the STM chip itself. And there is one more pin. This one will be connected to LCD command 0 line. This will be hooked up to oscilloscope to understand when LCD command line signal starts to be produced. We can find STM chip connectivity details on the middle part, but in this video we'll not solder it down to our PCB, as we will be using STM32 chip from NUCLEO board itself. And on the left side you can find Titan driver and LCD connectivity details. Please note that custom symbol and footprint have been designed here. This you can take from my GitHub project. The link I will keep under the description below. You can notice we use a potentiometer here, forming a voltage divider. This is used to drive the LCD pin, which is responsible to adjust LCD brightness. We will power driver chip with 3.3 volts, but our LCD is designed to run on 3.0 volts, so the brightness reduction is a necessity here. Let's switch now to our PCB layout design. This has quite simple routing. It just contains 2 layers. And there is a principal measurement here which we have to follow. The distance between socket connector pins should be exactly 2300 mils in total. This way our adapter PCB will be pluggable into NUCLEO board without any issues. Here we can see the footprints are placed, used for our Titan LCD driver, potentiometer to adjust the LCD brightness, LCD component itself, and our Nucleo board connector headers. Now let's check our PCB 3D viewer. On the bottom side we can find our dev board connectors, and all other components are placed on the front layer. You can notice header with trio pins located here. This will be used for a jumper placement in the future, to switch between flash and run boot modes applicable to STM chip onboarded. And whenever you will be placing LCD component itself, this edge marker orientation should be preserved. Now we can export our Gerber files and submit it to GLC PCB for manufacturing. Here I've got my PCBs manufactured and delivered, so let's open them. This time I have decided to order white color, and overall PCB quality is not bad here. There are 5 of them in total, but I will be using just 2 of them. One will have all LCD components and connectors populated, except STM32 microcontroller itself. This way we can plug it into Nucleo board, and we can debug everything using Nucleo STM32 chip. Another PCB will have all components populated, including STM microcontroller, so here we could drive our LCD independently from Nucleo board. Now let's start with LCD component soldering. Let me place it here. We also have to take proper positioning into account. This is a through-hole component with 2 mm pitch size. This way we'll be following standard through-hole soldering procedure. Nothing special here. Now we can use key-type soldering tip just to remove any excess solder around the pins. Once soldering is done, we can trim these legs, but I would like to keep few of them on the top row, exact pins which are connected to 4 common lines. Here I have connected them together, and we can use it to make basic LCD testing. They will be connected to 3 volts common level, which can be produced by simple voltage divider. LCD signal pins at the same time can be connected to square wave generator. Here I have created basic oscillator using 555 timer. This should produce output square wave with around 256 Hz frequency. Potentiometer can be used here to adjust the frequency, so let's adjust it accordingly. You also can replace this 12 kΩ resistor by another potentiometer, just in case of you will need to fine-tune the duty cycle to set it to 50% exactly. Peak-to-peak amplitude is 6 volts here, but in relation to 3 volts common line level, it is varying between -3 volts and +3 volts, which is perfect for our LCD to drive the segment. All common lines are connected to 3 volts output now, and whenever we are trying to feed square wave into specific signal pin, we can see that corresponding segments are getting ignited. This way we can make sure that all segments are working fine here. Once testing is done, we can trim unnecessary pins. It's time to switch to our LCD driver, and we have to pay extra attention here in terms of component positioning. First pin marker should be on the top left side. Now let's solder it down. All components are soldered, and you can notice I have placed potentiometer here. This can be used to adjust LCD brightness. Also, I have soldered 2 capacitors here, C1 and C5, so we can have a proper debouncing here for count and reset buttons. And let's place buttons themselves. Now we can plug adapter PCB into our host board. This will give us opportunity to debug everything using CubeIDE, where SWD debug session can be established. So we could set breakpoints and look up actual variable values in runtime. And overall alignment looks quite good here. Also, I will need to solder one wire to this pin. This way we can use oscilloscope to monitor output COM signal, which will be coming from LCD driver. So the final setup is completed now. This will help us to make debugging. And here you can notice corresponding wires connected to oscilloscope. This way we can track driver's output COM0 signal. This is our CubeIDE sample workspace, and within main C file we can find all necessary logic. We are starting with GPIO pin numbers definition here. Once we'll start to use standalone STM32 chip instead of NUCLEO board, these pin numbers will have some differences. And within CubeMX application, we can notice these pins configuration. One of them is set as input. This will be driven by count button, and we have to set it up to pull-up mode. 3 output pins also have been defined. This will be used to control LCD driver. Timer 6 also needs to be enabled as well. On a later stage, once we'll use the second application sample with ticking counter. And here we have LCD drivers comments themselves. This is configured based on datasheet specifications, which we have reviewed previously. The next is LCD segments matrix definition. This will specify which exact 7 segments display elements needs to be ignited in order to show specific digit. Now we can notice these 3 display methods, which will just place corresponding symbol under specific LCD digit position, and the general method to display the number. Here we'll extract first, second and third digits accordingly, and we'll place them into corresponding LCD digit positions. Everywhere we are using put matrix symbol method. This will take data from our symbols templates array and will place it into LCD matrix buffer. Submit matrix method then will use this buffer to transfer display data to Titan LCD driver. Here I have initialized STM debug session and will be following the specific command sequence. These commands are specified under official datasheet, as I have shown before. So let's execute first 2 commands. Now system is enabled and BIAS generator is also initialized. We don't see any difference here on oscilloscope with common signal. Then let's switch on our BIAS generator, and as we can see, COM0 signal is generated now, the same way as it was specified under our datasheet. As the final step, let's try to transmit number 235 to LCD driver. So here we can see this number has been displayed successfully. This way you can use this sample to display any symbols which are required by your application. Here I have built a simple timer which makes incremental count. You can download sample main C file for this application from my GitHub repository. All links are provided in the description below. You also can find KiCad PCB design files over there. Please leave a comment below in case if you have any questions. I hope this LCD drivers introduction video was useful for you. Thanks for watching this video. See you next time.